So today we are going to start a new topic that is multiple input and multiple output, or in short, MIMO systems. So we will be talking about systems where we have multiple transmit antennas and we would have multiple receiving antennas. So in the last topic we have been talking about diversity combining, and we already had multiple antennas placed at either the transmitter side or the receiver side in order to improve the performance under fading. So that topic was diversity combining. So in diversity combining, we had multiple antennas at say at the receiving side, and we have to intelligently combine the outputs of those multiple antennas such that we get a performance gain, right? So typically we had multiple antennas at the receiving side which received different received signals, and then we multiplied a gain associated with each of those antennas such that if we combine these in an intelligent manner at the combiner output, that means at this point the signal to noise ratio gamma sigma is much better than the signal to noise ratio of the individual branches. So these branches, and we had capital M of those branches, we said that we would get an array gain in terms of the improvement in the signal to noise ratio, uh, and we would get a diversity gain in terms of the performance of the bit error rate or the outage probability curve. So that was diversity combining. That required one aspect which was co-phasing. So we said that if we have a complex number being received at each of these multiple antennas, and if we want to combine them intelligently, the first step should be that we should be able to co-phase all of these inputs such that we get a gain out of it. So we get, if we get a received signal, say R1 e to the power j theta 1 like this, then this we said that the phase of the gain AI must be equal to minus the angle of the ith received signal which was received at the ith antenna. For example, if this is the second antenna, the received signal here would have a magnitude R2 and it would have a phase of theta 2. So if we multiply this signal with something that has a phase of minus theta 2, that would mean that this would get aligned along this axis on the x-axis. Similarly, if all of these branches are multiplied with complex numbers which has a gain of minus of what has been received, that would mean that would co-phase all of these received signals along this x-axis. So this co-phasing brought you two gains, right? So one gain that we talk about was array gain. So array gain referred to the improvement in the signal to noise ratio at the combiner output. And then it also brought you what is called a diversity gain. And the diversity gains refer to the improvement in the performance curve. We would formally define diversity gain later on in this topic when we would do a comparison of what is called the comparison between the diversity and the multiplexing gain. So there would be another gain associated with it. So we'll come to that in a minute. So the question that we would have here is, can we improve the throughput or increase the throughput of our system with the help of these multiple antennas? So for example, these multiple antennas have helped us to improve the signal to noise ratio. That would mean that you can make use of higher order modulation schemes, and you can achieve a similar bit error rate performance as compared to SISO, uh, such that, and if you are using higher order modulation schemes, um, then you would be increasing the throughput of the system. So one way of increasing the throughput of the system would be to make use of higher order modulation schemes, as multiple antennas at the receiver have allowed you to get an improved signal to noise ratio. So the main question is how to increase the throughput. And one way is um, use higher order modulation schemes, as we are getting an improved signal to noise ratio. So we would be able to make use of higher order modulation schemes, as typically higher order modulation scheme require higher signal to noise ratio to achieve the same bit error rate performance. And as you would get that gain from diversity combining, so you would be able to make use of higher order modulation schemes for a given bit error rate performance. So that is one way to improve the throughput. Another way, which is probably a more direct way, is can we multiplex our symbols, right? So second way, so this was the one. Can we multiplex our symbols? What does it mean? That means if we have multiple antennas at the transmitting end, multiple antennas at the receiving end, can we transmit independent data streams, right? By transmitting independent data streams from different antennas. And the answer to this is yes, that we can multiplex, or in other words, we can transmit multiple data streams from different transmitting antennas, and that would increase the data rate by the number by the number of data streams that we would be able to transmit over the system. So that is called multiplexing, and the gain associated with this would be multiplexing gain. So that would be multiplexing. So we would be going toward that. How can we multiplex our data? How can we transmit multiple data streams over the system? For that, first let's look at the system model for the MIMO for our MIMO system. So we have seen our system model for the combiner. So for the diversity combining, this was our system model at the receiving end, for example. So you had multiple branches starting from one first antenna all the way to mth antenna, and then we multiplied each of these branches with their respective gains and combined them together. So now let's look at the system model for the MIMO system. Right? So we have multiple antennas at the transmitting end. And the number of transmitting antennas, let's suppose that we have MT number of transmit antennas. This is antenna 1, this is antenna 2, and we have MT number of transmitting antennas. Similarly, we would have multiple receiving antennas, and in total, let's suppose we have MR number of receiving antennas. Right? So this is our system. This is the basic setup, and now each of these antennas would be interfering with each other. So we would suppose that we are in the narrowband fading regime. That means the received signal at transmitted once it is transmitted from one of the antennas, it is received at all of these antennas, but it is in the narrowband regime. That means it is just a scaled version of what has been transmitted. So that is what we would be assuming. So if the signal is transmitted from this antenna, so it would get received by the antenna 1, it would get received by the antenna 2, it would get received by all these MR receiving antennas, right? And similarly, the signal that is being transmitted, say, by this mth antenna would get received by the antenna 1, would get received by the antenna 2, and would get received by the MRth receiving antenna. So the channel gain associated with the first receiving antenna so would be called H. So the channel gain between the first receiving antenna and the first transmitting antenna would be H11. So the gain for this part would be H11. The gain for the first receiving antenna and the second transmitting antenna would be called H12. So suppose if the signal is transmitted by this and received by this signal, so this gain would be H12. Similarly, the gain for this path, which is the mth transmitting antenna and the first receiving antenna, would be H1mt. So you can imagine that it is kind of a reversed order. So if Hij is the gain of the channel, so this gain is for the ith receiving antenna. It is the channel gain between the jth transmitting antenna and ith receiving antenna. Right? That means Hij connects. So if this is the input and this is the output, so it would mean it connects the jth input with the ith output. So that is what it is. And because we would want this to represent in the matrix form, and that is why this notation is used, because that is how your matrix algebra would work. That this Hij would be the coefficient that would get multiplied with the jth input and the ith output. So that is how it is. So let's try to. So this is our system model that all of these antennas are transmitting signals, and every signal transmitted by each of the antenna is received by all of these MR receiving antennas. So if you want to write down the system of equations for this particular system model, let's try to write down the system of equations. So suppose we want to write down the equation for the received signal at the first received antenna. So the received signal at the first receiving antenna would be y1. That would be equals to h11 times x1. If x1 is the input signal transmitted by the first antenna, plus h12 times x2, where x2 would be the signal transmitted by the second antenna, and all the way to h1mt times xmt, right? And then of course you would have the noise terms. Let me call it n1. Similarly, the received signal at the second antenna would be h21 times x1, plus h22 times x2 plus h23 times x3 plus h2 empty times x empty, and plus you would have some noise term, and this would continue, and you would have mr number of total total received signal, because you have mr number of received antennas. So your ymr would be equals to h mr times 1 x1 plus h mr times 2 x2 plus h mr times mt times x mt plus x plus noise term, and that noise term will be mr and mr. That would be the noise term for the mrth received signal. So that is your system of equations, and here you can see clearly that, for instance, if you talk about this channel H23, so this channel is connecting the second output with the third input X3. So your output is Y2, this is your second output, and your input, the input is the third input X3. So H23 connects the second output with the third input, right? So this is how it works for the if you want to write this down in the matrix form. And now you can represent this in the matrix form, and it's obvious that how would you represent that. So your received signal y can be represented into a vector form. So you would have a vector y1, y2, ymr would be equals to this channel matrix h11, h12, h1mt, h21, h22, h2mt, hmr1, hmr2, hmr So you can see that this channel matrix has a dimension of mr cross mt, where you have mr number of rows because you have mr received antennas. So this has a dimension of mr cross mt that would get multiplied with a vector x1, x2, and you would have xmt, that would be equals to the number of columns of this matrix. So this, you have empty number of columns in the channel matrix. Let's call this channel matrix as H. This is H, and this is element of R mr cross mt. Right? So this and this, so this is a matrix. This vector X is called your input vector, and that would be equals to R mt, where mt is your number of transmitting antennas. Plus, of course, you would have your noise vector, and you would have N1, N2, and MR noise terms. So this is your vector Y, this is your vector X, this is your vector M. So you can see that you have this system where each of the term was interfering with each other term is now clearly represented in terms of the matrix, and in other words you can write it in a single line, right? So this can be written as y vector is equals to h matrix times x plus noise vector, right? Where this y, h, x, n all are complex numbers. These are complex numbers. So when I'm saying this R, so this is not R, so these are complex number, right? So these are C. And similarly, the dimension is empty, but this is C. These may be complex numbers. Um, so in general, we would take them to be complex numbers. So you have MR, the dimension of Y would be MR cross 1, this is MR cross MT, X would be a column vector of dimension MT, and noise you would have MR number of terms because you have the same number of noise terms as the output terms. So that is your system model. And now let's talk about for a moment about this noise term. So this noise term is of course would be assumed to be a additive white Gaussian noise. So this noise term, because noise is a random process, is typically characterized by its covariance matrix. So the covariance matrix of the noise is defined as expected value of n times n Hermitian. That is the covariance matrix. And remember that for any vector v Hermitian is nothing but v conjugate transpose. That is what we mean by the Hermitian. So this is so if n is a column vector of dimension mr cross 1. So this would be a row vector of dimension 1 cross mr. And hence what you would be doing here is the outer product of a column vector with a row vector, and hence you would get a matrix here. So this covariance matrix, expected value of n times n Hermitian would be equals to the expected value of n1 conjugate, expected value of n1 times n2 conjugate, right, times expected value of n1 times n mr conjugate, right. Similarly, this second term would be expected value of n2 times n2 conjugate. Last term would be expected value of nmr times nmr conjugate. This is nothing but the noise covariance matrix. You would fill in these gaps. So this would have a dimension of mr cross mr. So you would have mr number of rows, mr number of columns. It would be a square matrix, and we would assume these noises which are added onto different antennas to be independent Gaussian processes. That would mean that if they are independent Gaussian processes, if you take the expectation of Ni, Nj, so if Ni and Nj are assumed to be independent, then this would mean that expected value of Ni Nj conjugate would be equals to 0 if I is not equals to j, and if I is equals to j, this would be equals to its variance. So because we have assumed the noise to be independent and identically distributed. Right? So these noise terms are independent and identically distributed. So for all I for all these terms, that means these variances in the diagonal term for all of these noise terms is equal. So this means you can write this covariance matrix of the noise. That means you can write this expected value This is the reason. Okay, so now we can write this expected value of n in Hermitian as so you would have sigma 1 squared here, sigma 1, sigma squared here, sigma squared here, sigma square here. So all the diagonal terms would be sigma square, and you would have a 0 in non-diagonal terms. Right? So this is your noise covariance matrix, and you can see that you can write it as simply this can be written as sigma squared times an identity matrix of dimensions mr cross mr. Right? So this is your noise covariance matrix. So in a similar manner, you would have an input covariance matrix. This is and this is your noise covariance matrix. Similarly, you can have your input covariance matrix. Remember, you have MT number of transmit antennas. Right? So now if we talk about the input covariance matrix, so your input is vector x, and if you compute expected value of x Hermitian, that would give you what is called the input covariance matrix, and typically defined as RXX. Um, so this input covariance matrix RXX would be equals to expected value of x1 conjugate, expected value of x2 conjugate, expected value of xmt conjugate. Similarly, expected value of x1 x2 conjugate, expected value of xmt x1 conjugate. Similarly, this would be expected value of x1 xmt conjugate. So this you can see that it's a this is a matrix of dimension mt cross mt. And the important thing that you can notice here is that these diagonal elements, so this element is nothing but the average transmitted power by the antenna 1. So this would be the average transmitted power by antenna 2. This would be the average transmitted power by the antenna MT. So if you compute the trace of this matrix RXX, that would give you the sum of total average power. And if you have a transmit power constraint, that means your total average power at the transmitted side should be less than or equals to some value p. That should mean that in the matrix term, you want that TR is for the trace of this input covariance matrix RXX must be less than or equals to the total transmit power constraint P, or in some textbook it is used as a rho, right? So that is your input covariance matrix. So now we would talk about how can we carry out a decomposition of this system model, which is a convoluted system model. Every input is connected to every output, and every output is connected to the every input. How can we decompose such a system into a bunch of parallel parallel signals or parallel streams, right? So what we want is that instead of having this as your transmission model, you want to convert this system model into a model where you have parallel streams. That means you want to convert a system where you have, for example, antenna 1, and it is connected to an antenna at the receiving side. Then you have another antenna here that is connected to the antenna at the receiver side. And you can have few of these parallel streams. So as you would find out that you can have a total of RH parallel streams, and this is the equivalent channel. So this is the equivalent representation. So we want to have a parallel decomposition, right? So we want parallel decomposition of um, of the system, a parallel decomposition of the MIMO channel, I would say. That means you want a system model where you have this kind of a system model where each of these antennas is connected to each of the receiving antennas. You want to do some signal processing at the transmitting side and at the receiving side such that this system model converts into this equivalent representation, that where you have RH number of parallel streams that you can transmit in parallels. And if that can happen, then you would get a multiplexing gain of RH. So remember, RH is nothing but, for a full rank channel, it would be minimum of MT comma MR, where MR is the number of rows, MT is the number of columns. So your rank of a channel matrix, if it is full rank, it would be equal to the minimum of MT MR, or in other words, it is the number of independent number of rows or columns of the channel matrix. So if you have a full rank matrix, then you would have a minimum of MT MR number of parallel streams that you can have, right? So we would start learning about the parallel decomposition in the next video.